Fucking Right, hello. Let's try and get through some problems here today. I think I might leave the camera off for today. Sort of felt and looked better. All right. So, what I'm gonna do today is I set some problems using the stuff from yesterday and a little bit from the videos today for the lecture for today. And that's because sort of today's lectures and tomorrow's lectures are sort of over the same thing. They're both about double integration. So I figured, give sort of the double integration stuff a little time to sink in. And then we'll do the more complicated examples for that tomorrow. And also, those of you wondering about the exam, so tomorrow's material, tomorrow's material will be sort of the cutoff for that. So basically just up through sort of this intro to double integration here. And what I'll do for the exam is post like several timed assignments on WebAssign. So kind of break the exam into chunks, and I'll post that probably at the start of next week, and then you'll have I want to say I'll give a week to do it, so they'll all be due on April 14th. So sort of get to each part. I'll break up the topics for this exam into a few chunks here, and I'll give you sort of an idea of what those different chunks are, and then there'll be sort of a timed assignment for each of those chunks. So I'll hopefully by the end of today get some like some samples of what that could look like up, so you can see how a timed assignment works. But it's basically just from the moment you open the assignment, you're going to have, however much time to do those problems in the assignment. Great. So let's go ahead and get started here with these problems. So problem 1. Right. So problem 1, these are just find and collect. Yep. Yep, go ahead. Ah. So I'm glad you asked that, actually, because I forgot to mention it. I think I said this sometime last week, but my idea for that is, give you a few attempts at it, but then sort of like each wrong attempt deducts a certain amount of the maximum points to it. So I want to give several attempts, but so I'll see sort of how fast that should reduce. Like, I don't want one wrong answer to like destroy a question. That just wouldn't be fair, I think. But then I also want to see if I can get sort of on both ends, like if you at least try it, even if you never get it right, if you at least try it, you get some amount of the points for it. And then if then based off like how many times you got it wrong, like take off a couple points for each time. That's probably the best way to do partial credit through WebAssign like that. It won't be 100. I'm kind of deciding back and forth between, like, 10 attempts and having the score decrease by like 10% each time, or something like 15 attempts, something like that. But I think I'm going to make the baseline probably like 20% of the points if you've at least tried it. But I need to see how I precisely set that up through WebAssign. All right. All right. Okay. So let's go ahead and get to the problems here. Sorry. So for the problems, for problem 1, right, we're just finding and classifying critical points here. So this is where we want to use the gradient to get our critical numbers, and then we're going to it's really critical points, I should say. We use the gradient to find the critical points, and then we use the second derivative test to, classify them. So, number 1 here, we have f of xy equals xy e to the minus x minus y. Right? So we want to find critical points of this. So step 1 for the critical points, ETS for points. For the critical points, we want to take the gradient and set it equal to the 0 vector. Okay? So in this case, our gradient, we need to differentiate with respect to x, so there's going to be a product rule coming in here. We're going to get y e to the minus xy when we differentiate, when we do the product rule, we can think of it as this part times this part. So that's the derivative of the first times the second, and then we need plus the first times the derivative of the second, which is the derivative of the second here is just negative of this. So we're going to get minus xy e to the minus xy. X minus y, sorry. All right, so that's the derivative with respect to x. And with respect to y, it's going to look pretty similar. Oh, did it over here too. Minus x minus y minus xy e to the minus x minus y. All right. So this will be our derivative, or our gradient. Okay? And this is what we want to set equal to the 0 vector. Right, so set this equal to 0, 0. So what we're doing then is we're solving two systems, or a system of two equations. Right, so we have this equals 0, and we have the second equation like this. I keep wanting to write xy there. Oh my god. I'm going to keep doing this. All right, there we go. So we have these two things, and we need to solve this system. Now, this looks a lot more intimidating than it actually is. All right, and the reason is that e to the minus x minus y, this function right here, because it's an exponential function, it can never be equal to 0. And in fact, in this case, it's always positive. So what we can do is divide both equations by that. So e to the minus x minus y. Right, and the reason we can do that, we always have to worry, like, when we divide by something, do we ever divide by 0? But again, this function's never equal to 0, so it's perfectly fine to divide by it. And then now our equations turn into this. Which is a little bit nicer. Right? So now that we're here, we need to solve this. Right? We need to solve both of these equations. Now, this is a nonlinear system, so we can't just use our, nice linear algebra matrix stuff, unfortunately. But that's okay. Right? What we're going to do is just tackle it one equation at a time. So if we look at these two, right, call this 1 and 2. Equation 1, let's start with this. So here, I can factor out a y, and then I get 1 minus x equals 0. Now let's think about what makes this equation here true. When is this true? Well, this equation is equal to 0 if y is 0 or x equals 1. Right? Just our standard, kind of think of how you find roots of a polynomial, right? You factor it and set the individual parts equal to 0. So that's what we're doing here. Okay? So these two values individually would make this equation equal to 0. Or sorry, this left part equal to 0, make the equation true. So what we have to do then is, for this case and for this case, see what needs to happen in the other equation. Okay. So for y equals 0, what needs to happen there? So let's go back to equation 2. The equation 2 is x minus xy, right, which is now x minus x times 0. And that needs to equal 0. Right? But this is just telling us that x has to equal 0. Cool. So this means, altogether, that we have 0, 0 is a critical point. Right? Because again, we say, all right, well, if y is 0, what needs to be true about the second equation? And the second equation boils down to x has to equal 0 for it to be true. Right? So that's one critical point. Now let's look at the case when x has to equal 1. Right? When x equals 1, again, we're going to look at the equation for 2. Plug in x equals 1. And so we get that 1 minus y has to be 0, which says, all right, well, y needs to be 1 here. So this tells us that 1, 1 is a critical point. Right? So we have our two critical points. So critical points, they are 0, 0 and 1, 1. Okay. Any questions thus far with that? So again, all we did here was we took the gradient and we're trying to get both components to equal 0 at the same time. So what we've done here is we've essentially said, all right, let's take the first component of the gradient and set that equal to 0 and see in what different ways can it equal 0. Right? And then once we have that information, which for us is y equals 0 or x equals 1, in each of those cases, right, in every single way the first one can be 0, we need to take that and then look at the second equation. In that case, how does that have to be 0? Right, so we have to do it for y equals 0, and then we have to do it again for x equals 1. Right? And if we had, say, a third way for this to be 0, we would take that, plug that into the second equation and try it again. Right? Because what we're trying to do is make sure that both equations are 0 at the exact same time. All right. So now that we have our critical points, now we need to move on to classifying these critical points. So there's a couple things we need. All right. So what we need to classify critical points is the second derivative test. Because remember, what we need to look at is this sort of d, which is the determinant of the Hessian of f. Right? If you remember that, that's this determinant with all the second derivatives in it. Right? So we need this expression, right? Which is, fxx, fy, fyy, minus, since fxy and fyx, these are going to be the same because we can only do this test on continuous enough functions. We can actually just write fxy squared here. So we need these second derivatives, right? So let's compute these. So remember, we already did we already did the gradients, or the first derivatives here. So let's go ahead and rewrite those. Y e to the minus x minus y minus xy e to the minus x minus y. And then fy will be x e to the minus xy minus y minus xy e to the minus x minus y. Okay. So let's go ahead and find these second derivatives here. So I have fxx. So derivative of this first part with respect to x, only this second part matters. So we just get this. Now this one's going to be another product rule. But the nice thing here is this is just the original function. So I can just write this. I know that's got to be derivative of that part. So this simplifies a little bit because these two can combine together. Give me minus 2y e to the minus x minus y. And now I'm going to get plus xy e to the minus x minus y. Fyy is going to follow a similar trend to this one. So we'll end up with this. That's what fyy will end up being. And then we need fxy, which is, let's see, differentiate this with respect to y. E to the minus x minus y, minus y e to the minus x minus y. And then over here, we're going to have minus x e to the minus x minus y. Actually, I should put a parenthesis here. And then minus xy e to the minus x minus y. Right. So it's a lot of stuff going on here. But let's simplify this a little bit here. So fxx, I want to factor out this e to the minus x minus y stuff so that this looks sort of less bad. Right? And then same thing, fyy. Yep. Oh, right, I keep forgetting I have... Yeah, what's up? Any particular one, or... Yeah, so these things, you know, xx, yy, xy, all we're doing is we start with these first derivatives we already have here, the ones that we computed for the gradient, and then we just have to take their derivative again. So just pretend this is now our new function. Fxx is going to be the derivative of this one, fx, with respect to x. So we just redifferentiate this function with respect to x, and that'll give us fxx. Right, so here when we do that derivative, you know, the y is just a constant, so we just bring that down. When we differentiate this part, we from the chain rule, the negative comes out, so that's this minus sign right here. And then since it's an exponential, the rest of this just sort of stays the same. So that's the derivative of the first part with respect to x. In the second part, this is a product rule again. So this is actually the same derivative we did to get fx, but so again, when we look at that one, there's two pieces, these two right here. So when we differentiate this, we have to do the product rule. So if we differentiate the xy with respect to x, that just turns into a y, and then we leave the second part. And then for the next part, so we it would be plus, here's the first function, and then times the derivative of the second. But remember, the derivative of the second is just going to be negative e to the minus x minus y. So that negative is right here, and then e to the minus x minus y. So this is derivative of the first times the second, and this is the first times the derivative of the second. Right? And then it's the same thing for all the others. For yy, it's just going to be the derivative of fy with respect to y. And then fxy, here I did it as the derivative of fx of this one with respect to y. So you would need a product rule on both parts. You could also, since this is a nice enough function, you could also, if you wanted, take fy and do the derivative with respect to x. Just as long as you mixed which derivatives you did, that's all that matters for this one. Right? Okay. So that's in the exponent, right? There's nothing that'll cancel out with. Oh, no, yeah, it's negative x minus y up there. Right? Uh-huh. No problem. All right. Cool. Yeah, this one, I wanted to pick an example that had multiple critical points to it. Unfortunately, this derivative is a little messy. So I wanted to pick something that was interesting to do, but fortunately the problem's a little messier than I was hoping for. But hopefully it seems useful. All right, so fxy. So here, I'm again going to factor this out, and we're going to end up with 1 minus y minus x plus xy. If we factor it out and then distribute that negative, we wind up here. Right? So now we need to compute this Hessian term, so what we often call d. All right? So d, remember, is fxx, fyy, minus fxy squared. So notice how each of these have this e to the minus x minus y in it. What I'm going to do is I'm just going to preemptively factor that whole thing out. Right? So I'm factoring that out of everything. I get one copy from here, one copy from here, and two copies from here. So this factors like this out of everything. And then, actually, maybe it's a good idea to just do this on a new line. Right? And then we get xy minus 2y times xy minus 2x minus this thing, 1 minus y minus x plus xy squared. All right, so we got a little bit of a big mess here, but it's not going to be that bad because the points we have aren't too bad. So what we need to do to classify these critical points is I like doing this in the form of a chart. So I have my critical point. Right, in this case, what did we have? 0, 0, and 1, 1? Yep. All right, so let's list out our critical points. Here we have 0, 0, and 1, 1. Okay. And then there's two things we need to look at here. Right? We need to look at the sign of D, whether it's positive or negative or 0. Then we need to look at the sign of fxx. Right? We need to figure out if that's positive or negative or 0. And then we can classify it. Okay. So let's get to it. So D of 0, 0. Okay. So if we plug that into this expression, right, we're going to have e to the 0 squared. Plugging it in here, we're going to have 0 minus 0 times 0 minus 0 minus 1 minus 0 minus 0 plus 0. Right? Lots of zeros in this one. So if you work all this out, this is actually negative 1. Right? So this is negative. And actually, at this point, we're already done. We don't need fxx because anytime D is negative, we know this is a saddle point. Right? So again, if you remember the test here, we need to think about, what is it doing? If D is negative, we always have a saddle point. If D is positive, then we look to the sign of fxx. Right? If it's positive, you're at a maximum or a minimum. If it's negative, you're at a maximum. And then if D is 0, then the test just fails altogether. Okay. Now we need to do D11. So this is going to be e to the negative 2 squared times, this is going to be 1 minus 2. 1 minus 2 times 1 minus 1 minus 1 plus 1 squared. Right? So nice thing here is all this is gone. That's all 0. Right? So we get, we get that this is, so e to the minus 4 times negative 1 times negative 1. And whatever this is positive. This is going to be a positive number because these two negatives are going to cancel out. So this is positive. So since that's positive, I actually do care what fxx of 1, 1 is. Right, so this is going to be e to the negative 2 times 1 minus 2. And this number is going to be negative. Right? And if fxx is negative, then this has to be a local maximum. Right? So you might remember from the second derivative test for single variable functions, remember we were interested in, taking critical points and plugging them into the second derivative. If it was a negative second derivative, we had the local maximum. If it was a positive second derivative, we had the local minimum. Right. So, and there we go. So this is sort of the answer here. Did I ask? Okay, I didn't ask for the values. Good. So this is all we had to do here is just classify these points. Okay. So It's a bit of work for that one, but any questions at all? Awesome. All right. So since we've actually spent a good deal of time here on this problem, let me go ahead and jump to part 1 from problem 2, just so we can get an example of this in here. Because part 2 of problem 1 is going to look exactly the same. Or it's going to be the same procedure. So let's go ahead and do problem 2. Turn black. There we go. Problem 2. Let's do number 1. Here. Right. So for number 1, we have this function f of x. Y is x squared plus y squared minus 2x minus 2y. Right? And R is this triangle with these vertices. So let me just draw R. Actually. 2. So R will be this triangle here. Yeah. Uh-huh. Yeah, you could use fxx or fyy. Either one is fine. Right? Uh-huh. Yeah, that's a nice feature. It has to do with how you actually have to build the pattern for this. Like, why use this D here? Why are we taking the determinant of this matrix of second derivatives? And if we were to do the second derivative test for functions of 3 variables, you basically see that you have to just start at either the top left or the bottom right corner of this matrix and just take bigger and bigger squares coming from that. I have a document written up somewhere with how to do this in general, which if I can find this, I will post it so you can see what the general second derivative test looks like. But we're just going to focus on 2 variables. And it's kind of nice, exactly as you pointed out, fxx or fyy both work. Unfortunately, we can't use the mixed partials. It has to be one of these 2. And again, that just has to do with how the theory works out. All right. Yeah, the second derivative test really is a really interesting tool that, if we had more time in the class, would be lovely to just spend a whole day on the theory of it. All right. Though, by the way, if any of you are interested, next semester when hopefully we're all back on campus, if any of you ever want to talk about the more general version, I would be absolutely happy to. All right. Where was I? Okay. So we want to find the absolute maximum and the absolute minimum of this function over this triangle. Right? So this triangle lives in the xy plane, and the graph of this function sort of lives above that triangle, or it might dip below it, but we want to sort of just imagine that we're only taking the piece of the graph that sits above that triangle. And what we're trying to do is pick out the highest point and the lowest point of that function. All right. So to do this, it actually should remind you of, how we found the maximum or minimum of a function on a closed interval, right? We found the critical numbers, plugged those in, plugged in the endpoints, picked out the biggest and the smallest thing. Here, we get to do basically the same thing. We find the critical points that are inside the triangle. Then since we don't just have endpoints anymore, we have sort of this boundary triangle. We have to find all the critical points that could happen on the boundary. Sorry. Okay, so let's start by finding the critical points. Critical points. Right, to do this, we just, again, take the gradient, like last time. Gradient of f. Differentiate this with respect to x. So we're going to get 2x minus 2. Differentiate this with respect to y. And we're going to get 2y minus 2. So, and we want to set this equal to the 0 vector, which is 0, 0. Now, if you look at what happens here, this means xy has to be 1, 1. That's the only way to make this equal to 0. Because if we set the first component equal to 0, we get that x has to be 1. And then if we set the second component equal to 0, we get that y has to be 1. So that's our only critical point, which thankfully is right here inside. Actually, let me change the color on that. Is right here inside the triangle. So we want to make sure that it's on the interior only, right? We don't want to take critical points that are actually on the triangle or outside the triangle, right? But it's inside, so we're good. So now we need to worry about the boundary. Right? So to do this, we need to come up with expressions for each of the 3 pieces of the boundary. So let me call these 3 pieces L1, L2, and L3. Right? Because they're all lines, so the signs for line 1, line 2, line 3. Right? So the easiest way to do this is to come up with a parameterization of the line, right? So we were finding these equations of lines. This will be the best way to do it. Actually, in this case, it's a bit simple to do it the other way. So here, L1, this is a vertical line here. So we're looking at the vertical line x equals 0, right? That gives us this y-axis line. And we need to look at the range of y values, which is from 0 to 2. L2, this bottom line here, this is the horizontal line, the x-axis. So this is the equation y equals 0. And here, x also goes from 0 to 2. Okay. So the idea here, when we're doing the boundary stuff, is we need to somehow cut down our function from 2 variables to 1 variable. And that should make sense because a line or a boundary is 1-dimensional, so we should only have 1 variable. Right? And then finally, L3. Here, right, the equation for this line is x plus y equals 2. And we need to decide, oh, sorry. Thanks for pointing that out. Sorry, I forgot to mute myself. Sorry about that. All right. So here, once we've done this, we need to decide what variable we want to solve for. And that means sort of like, should we use x as the interval here or y? I like solving for y. So maybe let's go ahead and solve for y in this. This is going to be 2 minus x. And so now x is sort of the independent variable, so I can say x goes from 0 to 2. And again, we're just looking at what x value does this line start at, what x value does this line end at. All right, so now that we have equations for the boundary, we want to sort of plug these in, each of these 3 into the function and search for critical points. So on L1, we have f of 0, or let me do it this way. I'm going to call this g of 1. Since x is going away, let me call this g1 of y. So this will be f of 0, y. Right? And if we plug that in, we're going to get y squared minus 2y. Right? So we're sort of maximizing this function on the interval from 0 to 2. So now we do the usual Calc 1 stuff here. So we take a derivative, g1 prime of y. Right? This is going to be 2y minus 2. And so we get that, and we want to set this equal to 0. So we get that y has to be 1. All right. So we get here sort of, I don't want to call this a critical point, so let me call it a candidate point. X has to be 0 here, and then y is 1. So that's another point we're going to test. Right? Do this for L2. This time, y is going away. So let me say this is g2 of x. I'm going to plug in the 0 for y. So I have x comma 0. And let's see, this will be x squared minus 2x. And again, from 0 to 2. Right? I need to make sure this number I find is inside this interval. Right? If I ever get a number outside of that interval, remember, we don't bother counting it. Okay? So g2 prime of x is going to be 2x minus 2. Set that equal to 0. This tells me that x has to be 1. And that's between 0 and 2. So we're good. So another candidate is 1 comma 0. Right? Y has to be 0 and x is 1. All right. Now we have one more, L3. So let's see, we've decided to solve for y here. So g3 is going to be a function of x, and it's going to be f of x comma, I'm going to plug in this expression for y, 2 minus x. Right, so we get x squared plus 2 minus x squared minus 2x minus 2 times 2 minus x. Right, so let's simplify this a bit. What do we get? X squared plus 4 minus 4x plus x squared minus 2x minus 4 plus 2x. Let's see, does anything cancel? Those cancel. Those cancel. Right, I think that's everything. So this is 2x squared minus 4x. Awesome. And now we just do the same thing that we've been doing. So g3 prime of x is going to be 4x minus 4. Right, set that equal to 0, and this tells us x equals 1. Oh, sorry, I forgot to write down the interval here. The interval is still 0 to 2, and x is in there. Now that I know what x is, I have to get y. So y, remember, is 2 minus x. That's going to be 2 minus 1, which is 1. So another candidate. Sorry, give me a second here. Oh, I messed up. Did I? I did mess up. Okay. This green dot isn't actually right here. All right. Sorry. So candidate is xy equals 1, 1. All right. So I did make a mistake earlier because my picture is poorly drawn. Back up here. So here, when we found the gradient and set it equal to 0, this is 1, 1, but the problem is that's not in the middle there. Despite my poor drawing, it should actually have been up here. So this is, we're not going to count this one because it's on the boundary. Right, it's on this line. It's on the line x plus y equals 2. Sorry about that. So we don't count it. But that's okay, because we're going to get it anyway from here. So we have a candidate point from each of these three edges, and we're going to automatically include the corners of the function. So what we're going to do is plug in all of our candidates into our function here. So here we have, we found 1, 0, we found 0, 1, we found 1, 1, and now we also need to plug in every single corner. So 0, 0 is a corner, 0, 2 is a corner, and 2, 0 is a corner. Okay. Now we're going to plug in all of these to the function. All right. So here, when we plug this in, we're going to get 1 plus 0 minus 2 minus 0. This is negative 1. If we plug this in, we get 0 plus 1 minus 0 minus 2, which is also negative 1. All right, plug in 1, 1. We're going to have 1 plus 1 minus 2 minus 2. Let me remind you what f is here. So I'm just plugging these points into that function. All right, so this is negative 2. Plug in 0, 0, and I get 0. Plug in 0, 2, get 0 plus 4 minus 0 minus 4, which is 0. And plug in 2, 0, I get 4 plus 0 minus 4 minus 0, and that's 0. So there's something quite interesting that goes on here, which is that all three of these are the absolute max. And this, actually let me use a different color here. This one here is the absolute min. So let's phrase the answer like this. F has an absolute min value of negative 2 at 1, 1, and an absolute max value of 0 at 0, 0, 0, 2, 2, 0. Right, so it's sort of smallest in the middle of the triangle, and in sort of the hypotenuse of the triangle, and then it grows as you get towards the corners, is basically what's happening here. Right? And that would be it. So these problems, they're a little drawn out. They take a little bit of work to them. They're not particularly difficult, I like to think. They do have a bit of work to them. So this is why I wanted to make sure that we worked through some of these. And I guess we'll save all the double integral stuff for tomorrow here. But yeah, it's important to sort of understand how these work. Right? So any questions before we take a break before the next class? Excellent. All right. So we'll be back in a little bit. But thanks for watching. All right. So, do some more math. I'm going to leave the leave the camera off today. Not feeling as well still, but could be worse. That's not supposed to be happening. All right. So, actually, let me just completely boot that app. All right. So before we get started with the problems, let me just say a couple things about exam 3 here. So the material from this week is going to be the cutoff for it. So the intro to double integral stuff, I kind of broke that over today's lectures and tomorrow's lectures. And I have some double integral problems on the problem set for today, but we only got through 2 examples in the first section, so I think that's probably all we'll get through here. But basically, the idea, what I want to do is next week we'll post some assignments that'll be considered the exam. So I'll break the exam into a few chunks. So, based off internet connections and things like that, and sort of giving people a chance to, get caught up on lectures to where they need to be. What I want to do is break the exam into sort of like chunks by topic, and then give like short timed assignments on each of them. I'm not sure how long each part will be just yet. Like time wise, probably something like 20 to 30 minutes, but we'll see. I need to figure out all the details I can set with the timed assignments here. But yeah, so it'll be broken up like that. And my goal here is to sort of say, not give you 100 attempts like the homework, but something like 10, 15, 20 attempts per problem. And each sort of incorrect attempt will deduct some percentage of the maximum score for that problem. And my goal here is to sort of say, not give you 100 attempts like... There we go. Sorry about that. So, yeah, each problem will have, some limited amount of attempts that each wrong attempt takes off a little bit. I also... Hopefully I can get it to sort of give a baseline score that as long as you attempt the problem, you get something like 20% of the points for it. And then kind of build from there. So this way there's some kind of resemblance of partial credit on it. Like I said, my plan is to put those up next week and then probably have them due on April 14th. So it'll give you some time to work on them, and hopefully that helps with those of you who are on different schedules or anything. I don't want to set it to just here's one day and you better be able to do it. It works a bit different with online, so hopefully having like I think like a week and a half or so it'll be to get through it all. Hopefully that'll be all right. Again, they'll have some kind of timing to them. Yeah. So hopefully that helps out getting the exams. Oh, the last thing I wanted to say about that is as soon as I can get this done, I want to post...
When do you plan on having exam 2 graded?
As soon as I can catch up on everything. That's on the list of things to be done. I think sort of like everyone here, we're trying to kind of scramble and get everything back in line. So I don't want to promise a date, but I got all the lectures up for the next 2 weeks for our class. Homework will be soon, so I should be getting that done in the next couple days, I hope. That should be coming up soon. But yeah, I feel bad. I'm so far behind on all that stuff. But I'm trying to get caught up here. So the same, right? I want to try as soon as I can, just so you guys have an idea of what it'll look like. Post some kind of.
I know this may be difficult, but is there any way that we'll be able to know where we made our mistakes on exam 2 also?
I want to try as soon as I can, just so you guys have an idea of what. Sorry, I was just waiting for my echo to stop there. So I have to figure out how I can do that. That is kind of tricky. Because if I were still able to go into campus, the plan was going to be that I could just scan these and send them to you guys. But since I can't go in, I'll see if I can get in just for a day or just for an evening to scan them real quick. Otherwise it'll be kind of tricky to do. Yeah. Let me see if I can get in just for a night to scan them. That's probably the easiest thing to do, I think. So hopefully that works out. Otherwise, I'll be taking lots of pictures probably.
I think there might be an app that you can get. I have an iPhone, and there's this app called like TurboScan or something that you can just scan it into a PDF. So
Okay.
if that might help you.
I'll have to see if Android has one of those. Alright, that doesn't sound like a bad idea though. Thank you. Alright. Where were we? Right. So let's go ahead and, like I said, I think we're just going to get through 2 examples today because these are,
Thank you.
while not terribly difficult, they do have a little bit of length to them. So let's go ahead and give it a go here. So I'm going to do example 1 from both problem 1 and 2. And then I think problem 3, those double integrals, I think we'll save those for tomorrow. So problem 1 here, we want to find and classify the critical points of this function. Right. So when we're trying to find critical points, what we're doing here is we're taking the gradient and we're setting that equal to the 0 vector. So gradient of f here, so we need both first derivatives. So take the derivative with respect to x. So this is going to be a product rule between these 2 pieces. Right, so we're going to have y e to the minus xy, x minus y. And then derivative of the second part will give us minus xy, e to the minus x minus y. Right, so this is derivative of the first times the second, plus the first times the derivative of the second. Again, derivative of the second pops out a negative sign from this right here, so that's the minus. Right, and then when we differentiate this with respect to y, it's still going to be another product rule, except this time the x survives in the front. And we're actually going to get the same thing here. Right, because we're going to differentiate with respect to y, so this negative comes out this time. And that's the gradient of f. And we want to take this and set it equal to 0, 0. right? So now that we have that, the next step is to try and solve this, right? So what we're doing is we're taking this first part, setting it equal to 0, taking the second part, setting that equal to 0. We have y e to the minus x minus y minus xy e to the minus x minus y. Set that equal to 0. And then x e to the minus x minus y minus xy e to the minus x minus y. Right? So we have these two equations here that we need to solve. Now, one nice thing here is notice every single piece here has this e to the minus x minus y, and that it's always positive. It wouldn't matter if it's positive or negative. All that matters is it's never 0. So what we can do then is just divide by it. And our new system turns into y minus xy equals 0 and x minus xy equals 0. Right, so we've just divided both equations by e to the minus x minus y. And again, we do have to make sure that we're not dividing by 0. Right, because if we're dividing by 0, we have to count that separately. But here, since that part's never 0, it's safe to divide by. Should one of the minus x be a y? Put 2 x's somewhere? I think we're good. Exponent should always be minus x minus y. These two should be opposite. Same. I think we're okay. I think we're okay. All right. So I'm going to call this equation 1 and 2. Now, when we're doing this, we want to, when we're solving these nonlinear systems of equations, it's a bit trickier than, the ones we were doing before spring break, right? Those are systems of linear equations. There's a nice, algorithmic way to do it. Here, that kind of all goes out the window, and you just sort of do your best. So the way I like to approach these is, I'm going to take this first equation, and we're going to solve that. See, in what ways can that be 0? All right? So equation 1 here, y minus xy, we can factor out the y, get 1 minus x, and then this is equal to 0. All right? So this tells us that either y is 0 or x is 1. Right? In both of those ways, we can get that first equation to equal 0. So what we have to do now is make sure that, we get everything. So we need to say if y is 0, what needs to happen in equation 2? And then if x is 1, what needs to happen in equation 2? All right. So we check those. We'll do this up here. So y equals 0, y equals 0. Let's check that. So what does equation 2 turn into? Right, so we plug in y equals 0, and we get, so x minus xy is going to be x minus x times 0. So that's just x, and that has to equal 0. All right, so there we go. If y is 0, then x also has to be 0. So we get that a critical point is xy equals 0, 0. Now we need to do the same thing again. So we finished this one. Now we need to do the second possibility, what if x equals 1? Right, then we're again going to look at equation 2. So x minus xy. This is now going to be 1 minus 1 times y. That's 1 minus y. And that now has to be 0. Okay. So this tells us that y has to be 1. So the critical point here is xy equals 1, 1. So those are our two critical points. Now what we have to do, now that we have our critical points for this, we need to run the second derivative test on this to see, is it a local maximum, a local minimum, a saddle point, or does the test fail? So remember here, there's two pieces we need to compute, and they involve the second derivatives. So the two things we compute, there's this d value, which is this determinant of this Hessian matrix we talked about. Right? And all that is just the matrix of all the second derivatives. So fxx, fxy, fyx, fyy. Right? And if we do this determinant, we get fxx times fyy minus, here for us, we're only going to deal with sort of nice enough functions. So fxy and fyx are going to be the exact same thing. So we can just write fxy squared. Right? So we need to know the sign of this, whether this is positive or negative or 0. And then we also need to know fxx itself. So let's go ahead and compute these three second partial derivatives here for our function. So fxx. Actually, let me start by doing this. Let me rewrite the first derivative so we don't have to keep scrolling up and down here. Okay, so the first derivative was y, well, that's semantic. I got it. So it's y e to the minus x minus y minus xy e to the minus x minus y. And we found that fy is x e to the minus x minus y minus xy e to the minus x minus y. Okay. So now that we've got that, we need these three second derivatives here. So fxx, we're taking the derivative of this with respect to x again. So this first part, we only have to differentiate this first chunk of the function, we only have to differentiate the exponential part. So that's going to wind up giving us a negative, minus y e to the minus x minus y. Then minus, if you look here, we're differentiating this with respect to x. And if you pay attention here, why did that happen? If you look at this part right here, this is just the original function. So the derivative is just going to be this again. Right, so we just copy that down. And this does simplify a little bit. So we can get negative 2y e to the minus x minus y plus xy e to the minus x minus y. Right? And then fyy, it's going to turn out that we're going to get something similar going on here. So this is actually going to be minus 2x e to the minus x minus y plus xy e to the minus x minus y. Right? And again, the way we know that is sort of look at how fxx worked out, and then fyy is basically the same thing, but there's an x out front here. So if you went through this whole computation, you would find it's going to be the same thing, just the x swaps to a y here. Right? Now fxy is a little more interesting. Okay. So let's take the derivative of this with respect to y. Now actually both parts of this get the product rule. Right? So differentiate this part, and we have e to the minus x minus y, and then minus y e to the minus x minus y. So that's the product rule on the first part. Now the second part, we're differentiating that with respect to y, so we know it's going to be this, because again, this is the original function. So, just little ways to kind of save yourself some work, if you can notice things like that. All right. So now we need to construct this d here. So d is going to be, again, fxx, fyy, minus f of xy squared. So we've got to multiply all this stuff out. One thing I want to point out is notice that I can factor out the e to the minus x minus y from all of these pieces. So let me do that so it factors out like this. I get squared because I get 1 from here, and 2 from this part. Okay. And then we can make this look a little bit nicer. Let me move this down here maybe. That 2 wasn't supposed to come with it. This will stay up here. All right, so fxx, so we're going to take the part of this that doesn't have the e to the minus x minus y, negative 2y plus xy. Same thing here, it's going to be minus 2x plus xy. Right? And then minus this thing squared, 1 minus x, or keeping it in the same order as up there, 1 minus y minus x. It's actually going to be plus xy squared. Right? So it's a big, messy thing, but it's not the worst thing ever. Right? Of course, one can always use Mathematica to compute this thing as well. Right? And we'll do some of that. I think the lab this weekend, or this Friday, I should say, will just sort of focus on like computing simple things here, not doing anything extravagant. Right? Since we sort of have a lot of new things we can compute. All right. So we have our d here. What we want to do, actually, let me just copy fxx real quick since we will need that. And so if we factor out that exponential part, it looks like this. So what we want to do is make a chart. So we want the critical point. Right? About the critical point, we want to know the value of d. Well, the sign of d, really, is all we need. Then we want the sign of fxx. And again, we could also use fyy. That's perfectly acceptable as well. And then here, we classify it. Right. So we had our two critical points, 0, 0, and 1, 1. Right, and we want to plug these into d and fxx. And we do d first because if d is negative or 0, we don't need to worry about the fxx part. So let's look at it. D of 0, 0. So here's d. Let's plug it in. We're going to get e to the 0 squared times 0 plus 0, 0 plus 0, minus 1 minus 0 plus 0 squared. So if you look at this, right, this whole part is 0. This whole part becomes negative 1. This is just 1 squared, so this is actually negative 1. So d is negative, so we don't care what fxx is because we know this has to be a saddle point. Right? Anytime you have this D, this determinant of the Hessian being negative, it's immediately a saddle point. Now we need to do the same thing for 1, 1. So D of 1, 1, right? Just a brief reminder of what that is. I can fit them all on the same page. Right? So this one, we're actually going to get e to the negative 2 squared times, here we have negative 2 plus 1, negative 2 plus 1, minus 1 minus 1 minus 1 plus 1 squared. So this stuff in here adds up to 0, so that's all gone, this part. So I have e to the minus 4 times negative 1 times negative 1. And again, I don't care what the actual number is here. I just care, oops, that this is positive. Right? So since D is positive here, I do want to know what is fxx. Fxx of 1, 1. Right, let's see, so that is e to the minus 2 times negative 2 plus 1. So e to the minus 2 is positive, 2 minus 1 is negative, so this is overall negative. So we get a negative fxx. And if you remember, a positive D value, but a negative fxx value, this means local maximum. Right? So, negative second derivative means max, positive second derivative means minimum. Right? And then this right here, this is basically the answer, right? Because all we're asking here is just to classify the critical points. Right. Now, if you want the values, you could give it like an overall critical point thing where you do sort of the x, the y value, and then the f of x, y value. I think this is what some of the homework questions are asking for. But yeah. The important part, though, here is just the stuff. Any questions? Okay. Let's go ahead and go on to the next piece now. So like I said, I want to go on to part 1 of problem 2 here, just so we can get an example of these different things.
Question.
Okay.
So
yep.
I think that.
Do you want to mute the stream so I don't come through twice?
I have a question.
Yeah.
So so the question asks us to find a critical point, but why we do those steps after that? I mean, we do the classification.
So what do you mean the steps after?
So you find the determinant of those things. I think we are only about to find the critical point, right? For that.
So for this first problem here, I want you to find the critical points and then classify what type they are. So the first part up here, what we're doing before this determinant stuff is we're finding the critical points. But then when we're classifying them is when we have to take those critical points and we have to plug them into these two things, into that determinant and into fxx. So
okay, fine.
I was just doing the work of plugging it in underneath that chart. You can put the chart at the very bottom if you want.
Okay, no problem.
Okay. Any other questions about that? Okay, cool. So, oops. So actually, let me go on to problem 2, number 1. Right. I think I got a little ambitious with how many problems I put on this problem set today. All right, so here we're trying to find absolute max and absolute min values of this function, f of xy equals x squared plus y squared minus 2x minus 2y over this region R. This region R is the triangle with vertices at these 3 points, 0, 0, 0, 2, and 2, 0. Okay, so R is in here. Right? So we're trying to, this should kind of remind you of, back in Calc 1, we did stuff where it was like, find the absolute max and the absolute min of this function on this interval. Well, intervals become closed sets in multivariable, so closed bounded regions. So we're kind of doing the same thing here. So we need to find critical values that are inside the region, and then we check on the boundary. So let's start by trying to find critical numbers, or critical points. Critical points. Right, so we need to take the gradient of f, which in this case is, let's see, 2x. This is gone, minus 2. And that would be gone. And then differentiate with respect to y. This is gone. This is 2y. This is gone. This is minus 2. And we want to, again, set this equal to 0, 0. So when we solve this, this one's actually a lot easier than the last problem to solve. 2x minus 2 equals 0. There's only one option. We can only have x equals 1 there. 2y minus 2 equals 0. There's only one option. Y has to be 1. So this is where the gradient is equal to 0. But that point, my drawing is a little off scale here. That point is actually right here on the edge. So we're not going to count it. So we don't count because it's on the boundary. Right? So we only want critical points that are actually inside the triangle, completely inside it, not on the edge of the triangle, but completely inside. Right? So if we got something like 1/2, 1/2, that would be a critical point that we would count. Okay. So now that we've taken care of sort of the inside of this triangle, we need to move to the boundary. So let me call these 3 edges here L1, L2, and L3. Right? And what I want to do is write down a description of these. Right? So I need to come up with equations for each of these here. That let me sort of plug the lines into the function, basically. So for L1, this line right here is exactly a vertical line. So it's actually described by x equals 0. And then now that we know what equation describes it, we want a range of y values here. So y is allowed to go from 0 to 2 here. Okay. Similarly, we can do L2. This is the horizontal line here. So y equals 0. And for this segment, x is allowed to go between 0 and 2. Right? L3, we need an equation for this line here. Right? That happens to be x plus y equals 2. Which we have to choose to solve for either x or y. At the end of the day, it doesn't matter which. But let me solve for y here. This will be 2 minus x. And since I solved for y, I need a range of numbers for x. So here, this line starts at x equals 0 and goes all the way to x equals 2. 0, 2. So now I have equations for all 3 pieces of my boundary. And I'm going to use those to try and find any critical points. Well, let me call them candidate points that could happen on the boundary. So for L1, I'm going to call this new function G1, and it's going to be of y. And we're going to get it by plugging in the equation for this line to the function. So when we do this, we get 0 squared plus y squared minus 0 minus y, minus 2y, sorry. So we get y squared minus 2y, and this is on the interval from 0 to 2. All right, and now we just do the Calc 1 stuff, right? We just take the derivative and search for any critical numbers on the inside. Now the nice thing here is I just need to keep track of critical numbers that are not on the boundary. I'm not actually plugging in. So G1 prime of y, this is going to be 2y minus 2, which says that y is 1. So our candidate here is going to be 0, 1. Right? Because x is 0 here, we got that y is 1. And we do want to make sure that y is actually inside this interval, not outside it and not on the edge. But 1 is in between here, so we're good. Right? Now we do the same thing on L2. This one's going to be a function of x. And again, we just plug in the equation for L2. We plug in y equals 0. So here we're going to get x squared plus 0 squared minus 2x minus 0. So that one's x squared minus 2x. And that one's on the interval from 0 to 2 again. Repeat the same thing we just did. So G2 prime of x is going to be 2x minus 2. Sorry, we're setting these equal to 0 here. And so x is 1. And again, that's inside that interval. So we get a candidate. In this case, it's 1. Y has to be 0 on this edge. Right. All right, excellent. Now we do it for L3. All right, so we've set this up to be a function of x. Y is equal to 2 minus x in this case. So we got to plug all that stuff in. Yep, minus 2 times x minus 2. All right, it'll be a good idea to simplify all this, otherwise it's going to be a nightmare to differentiate. So let's expand all this out. Minus 2x, another 2x, plus 4. Right. Let's see here. Yeah, that's good. Right. I think I made a mistake in the earlier class, actually. Oh, I did these backwards.
Shouldn't it be minus 2 times 2 minus x?
Yep. I think you said that right as I figured that out. Thank you. All right. Well, the good news is this part doesn't change. This stuff does, though. So this will be minus 4 plus 2x. Okay, good. I didn't make a mistake in the earlier class. I made it here. Yeah, so this is backwards, I guess, but it multiplies out to the same thing. Now, the good thing about that is those cancel and those two cancel. So it simplifies at least a little bit. We get a 2x squared minus 4x. And here, x goes from 0 to 2. All right. So again, just keep doing the same thing here. Differentiate this. We have 4x minus 4. We want to set that equal to 0. This says x equals 1. Now we need to get the y value. So it's important to remember, important to remember that y is 2 minus x. So it's 2 minus 1, 1. So our candidate here is 1, 1. So it's actually kind of a neat coincidence that this critical point from the gradient, which didn't count originally because it was on the boundary, we actually got it anyway through this procedure. Right? Actually, that's not so much of a coincidence. I take that back. That's not really a coincidence. That sort of had to happen. All right. So we got these 3 candidates here, these 3 candidate points. Now we're automatically always going to take any corners of our region here. So these 3 corners here, we're automatically taking those. Just like we automatically always took the endpoints when we're doing this in single variable calculus, we're automatically taking every corner here, because they're kind of identical. Right? So at this point, what we want to do is just write down our candidate and its value in the function f of xy, which as a reminder is x squared plus y squared minus 2x minus 2y. All right, so let's list out the points we just found. 1, 0, 0, 1, and 1, 1. And then we also want to list out the 3 corners, which were 0, 0, 0, 2, and 2, 0. Right, so all 6 of these are candidates for being an absolute max or an absolute min. Now we just gotta do all the fun work of plugging these into the function. Right, so this is going to be 1 plus 0 minus 2 minus 0. So that's negative 1. Plug in 0, 1. We get 0 plus 1 minus 0 minus 2, which is also negative 1. Plug in 1, 1. We're going to have 1 plus 1 minus 2 minus 2, which is negative 2. All right, now we plug in these. 0 plus 0 minus 0 minus 0 is 0. Plug in 0, 2. 0 plus 4 minus 0 minus 4 is also 0. And finally, plug in 2, 0 to that function. We get 4, 0 minus 4 minus 0, which is 0. So now, just like we did in single variable stuff, we want to look through this list, pick out the largest number, that's your absolute max, pick out your smallest number, that's your absolute minimum. So it would turn out that all 3 of these, because they're all the biggest number here, these are the absolute max. And the smallest number here, which is just this single negative 2, this is the absolute min. Right, so it's sort of a good idea to summarize these answers here and say f has an absolute max, not bax, max, at 0, 0. Sorry, I need to edit some things. An absolute max value, because we're asking for the values here, of 0 at 0, 0, 0, 2, and 2, 0. Okay. And an absolute minimum value of -2 at, was it 1, 1? Right. And then that's a good form of an answer here. Right. Okay. So those are some examples of these. I know we only ended up kind of doing one of each because these are a little bit lengthy, unfortunately. But hopefully here you can kind of see, like, they're not necessarily difficult problems. They're just, again, a little lengthy sometimes. So it's just a matter of sort of keeping track of all the pieces that you have. Any questions at all about this problem? Okay, cool. This ultra low latency is not as ultra low as as it would have left me to believe. So just wanted to make sure to give it some time there to wait. Yeah. So again, I'm hopefully this week going to be caught up with everything, at least for the next little bit here. But that's it for today. If anyone has any questions, please let me know now. Otherwise, have a good afternoon, and see you tomorrow.